Hello everyone, thanks for giving me your precious time to present to you my master thesis.
Recording here. Okay. Good morning, everybody. We are here in the thesis defense of Nilofar Mousavi. Okay. Here is the committee. I'm thanking all the committee that is present here. Is Dr. Miguel Guijon, who is co-advisor, Dr. José Luis López Salinas, who is member of the committee, and myself, Carlos Rivera, that I'm in the committee. Okay. Here we are in the thesis defense of Nilofar, and so we're going to start with the presentation. And well, go ahead, Nilofar, if you want to share the presentation, okay? Nilofar Mousavi is presenting the thesis defense for the grade of master degree in engineering science, okay? So, okay, Nilofar, go ahead.
Thank you, Doctor, for giving the introduction. Thank you, everyone, for joining our committee and giving me your precious time. I'm going to present to you my thesis defense for Master of Science Engineering, MCI, in Tec de Monterrey, and I would like to thank my advisor, Dr. Carlos Rivera and Dr. Miguel Guijon, for their guidance during this whole 2 years. I really am grateful. And also thanks for Conacyt for supporting us. My thesis defense is about passive cooling strategies and performance of low energy residential building in semi-arid climate conditions. So in short, how we're gonna present to you is at first we're gonna talk about the introduction. What is the problem that we face in this industry that we want to solve? And we also go through a little bit of literature review, the previous works that has been done, and the research opportunity and gaps that are found, and the objective of this thesis. And then we move on to methodology, the general work plan, and we talk about how we validate our simulation, our case studies, and then finally we move into the results and conclusion and recommendation for future works. So in the beginning, in the introduction, I would like to state the problem in the building industry. Building industry globally is responsible for 40% of total energy consumption, and also 30% of greenhouse gas emissions is due to building industry construction and also consumption in buildings. And what's worse is that this demand is going to increase by 2100 by 350%. Because of global warming, we're gonna need there will be a higher demand for cooling. So this problem gonna get even worse. And in the Mexican context, buildings are responsible for almost 20% of energy consumption, which out of that 20% energy consumption in buildings, almost half, 45% is because of the cooling. And also another thing that makes this problem bigger is that Mexico, under Paris contract, they signed that they have a goal to decrease the greenhouse gas emission by 22% and 50% of carbon emission by 2030. So that's why reducing the carbon impact and energy is important in all industry, especially in building that has a big portion. So throughout the history, there have been a lot of solutions through passive cooling, which will reduce the need for using mechanical ventilation and electricity. One of the pioneers is Passive House Association, that they have a lot of suggestion and rule for different kind of buildings. But one thing about passive cooling is it's very climate sensitive. So you can't have one strategy that applies to all. So it needs to be studied in different climates. Some of the solutions that Passive House gave was applying thermal insulation or type of a window glazing that protects your interior spaces, airtightness. And some of them that we give an example here is like reflective paint, thermal energy storage materials like PCM, insulation, glazing, and external shading. To define some of the more advanced material that is used for passive cooling, first one is PCM. PCM is a material that has the temperature constant. When it has two states, from solid, it will morph into liquid. As you can see in figure 3 here, while the temperature increase, it's still in its solid form. it has a sensible heat, but once it reaches to its melting point, due to its latent heat, it has a higher gap for it to start changing state from solid to liquidify. And once the temperature outside reaches its melting point, it starts to liquidify. And when the temperature drops below its melting point, it will start to solidify and crystallize again. So you will get a cycle of delaying in the peak load hours of, for example, if the hottest hours is 3 p.m., it will become 4 p.m. in those spaces. And generally, there are two kinds of PCM. Some are organic and some are inorganic. If I want to talk about the industrial one that are available in the market, there are two main brands. One is Infinite R and one is BioPCM, where Infinite R is inorganic salt dehydrate and BioPCM is plant-based, but Infinite R is right now more available in Mexico. And another new kind of a technology is in glazing, which is low E. We know that generally there are three types of radiation, solar radiation, UV, ultraviolet, visible, and infrared, which out of that, we don't want the UV and infrared, but we need the visible light to come in. So what UV, low E glazing does is that it would decrease the amount of radiation from UV and infrared, but it allows the visible radiation in. So as you can see in the figure on the right, during a summer day, usually the low E glazing is applied in a double or triple kind of a glazing, and in a double glazing, it's on the inner side of the surface, and on the inner glazing, but on the outside. So once in the daytime it receives the solar radiation, it will reflect the ultraviolet and infrared, while it will allow the visible light to pass through. And during winter, what it does is it doesn't allow the heat inside the house to goes outside, so it reflects it back to inside, so it keeps the house warmer in winter and it keeps the house cold there in summer. And some of the literature review that we did, we studied more than 70 papers, but there is a short summary of a few of the examples of different strategies that was applied in the similar climate, which is hot and warm, because they have been studied in different kind of climate. They have used different methods, whether it's simulation or if it's experimental. And one thing that they had in common is how much energy they saved, or cooling energy they saved. Is that, for example, by applying low E glazing, they found that there could be a 6.4% energy saving in the building. Or by applying shading, we have 10% energy saving. And something that they were missing is that there was no cost analysis on how much they save based on cost. And then we come with a conclusion on the gaps and the things that was missing in all those studies. That one of them is that they are mostly limited to single or a few kind of scenarios. For example, only low E glazing or low E and reflective, but they don't combine the scenarios to see the impact of how it will affect the building. And also one thing that was missing was the economical study, but which I think is a very important if you want to, we know all the passive strategies, but it's not applied, because I think for the investors and for the users, it's very important to understand the economic benefit for them, how much of the cost they can return and how much they can earn from this the investment. So this was the important thing that we think is missing and we can do about it. And also, we saw that like it's very climate sensitive having passive cooling, and semi-arid climate was missing. And also in all those studies, they either call energy reduction or just cooling energy reduction, but there is a lack in analyzing the comfort analysis. How does it impact the comfort for the occupants, or how much of carbon they will reduce? So also another thing is that some of them are seasonal analysis, means they only analyze heating or cooling energy, whereas if they don't do an annual, sometimes maybe there is a decrease in energy consumption during summer, but in winter it reduces the energy consumption, and then the strategy is not applicable. So that's why we think that it needs to be annual strategies. So those are the gaps that we want to cover in our thesis. So the main objective of our thesis is to assist building developers and authorities with economical and environmental impact of applying the energy efficient configuration for passive cooling houses in residential houses, in Mexico. Beach also provide thermal comfort for residents, and also it's cost effective, which is very important. We also want to assess the thermal performance and carbon footprint of these scenarios. A scope of this work, with regard with the literature that we reviewed, and also with regard that available strategies in Mexico, we selected variables PCM, reflective paint, insulation, double clear glazing, and low E-coating glazing, reflective coating, and horizontal shading. And we want to analyze these variables around the parameters of energy efficiency, the carbon reduction, comfort analysis, and thermal behavior. So the methodology that we used in this study is mostly numerical through simulation, but we also try to validate it through experimental methods. So in summary, we have three main stages. The first one is data collection, which is we want to select the most the climates within Mexico and which one is more important. And also we want to find the common houses and select the cases study in Mexico. But in parallel, before we simulate those buildings, we want to understand whether our simulation is verified. So we selected two types of validation. One is through benchmark ASHRAE case 600FF, and another one is through an experimental chamber, which we had near Tec, and we tried to re-simulate the real data and the benchmark. And then once we see that our results and the other result is synced and is verified, so then we simulated in Design Builder our case studies as a base case, and then we tried different scenarios for the materials that we mentioned above, and we compared the result in terms of cost and energy. And if the cost and energy of the base case was more than the optimum case, so we will resimulate until we get the optimum result. So the main software that was used in this research was Design Builder with Energy Plus and simulation to understand the energy and comfort and thermal to estimate that. And also for us to resimulate the weather data for the experimental chamber, we needed to use transits because the data that we collect was global and we needed to have diffuse and direct radiation. We used transits to analyze that. And our first validation was through K600FF, which is the bestest ASHRAE free float test case. And this was a very simple geometry of 6 times 8 meter square house with 2 windows. And how we compare is the maximum temperature in the year, minimum temperature and average temperature, and we had the error rate of almost 0 and only 1%, which was verified through this benchmark. And then we move on to trying to simulate the real data that we had through our experimental chamber. We had near Tec, so we had a small unit, 2.2 times 1.4 meters square. And we had sensors inside, and also we had a weather station to record the weather data. And also we had ambient temperature, humidity, and surface temperature. And then we tried to simulate that chamber and compare our results. And for the error, we tried to use root mean error square and root mean square percentage error, which based on that, we only had 1% error, which was allowed because our Davis equipment that we use for the weather data had an error rate of plus minus 5%. So 1% was allowed, and we saw that our simulation method studies. So first thing was selecting the climate. So for selecting the climate, we look at the states of Mexico, which one has the highest cooling energy consumption. And we see that Nuevo León here is number 2. So it's one of the highest energy consumption in terms of cooling. And that's why we selected Nuevo León. And then we analyze its impact. Of course, Mexico has a few climates, 4 climates, 3 main climates. And Monterrey is in the arid, but it's a bit semi-arid climate. It's most part of Mexico has the arid climate, and Monterrey has the average temperature for the hottest months is 35 degrees. The number of hours that the temperature is above 25 degrees is 3,386 hours, which is almost half. And then the latitude is 25, humidity level is 65%, and the air speed is on average 3.4. And then after we selected our climate, we want to find the common residential houses in Mexico. So we went to RUV website, which is a Mexican housing government body. And we wanted to see how they classify the residential units in Mexico. And we saw that they actually classify it based on the people's annual average wage. And we also looking at the housing classes. We see how many, the percentage below shows how populated are those houses. So means, for example, for Economica, only 3% of total population lives there, whereas for B2 popular, 26%. So these three type together, they make up of 75% of the population of Mexico, which is almost third quarter of the whole population. That's why we selected these three types. And based on these three types, we know that B2 is a bit cheaper construction, and then B2 and B3, they increase in their construction. So when we want to define our buildings, we try to find the most common type of construction in Mexico. And also we want to cover almost all kind of available houses in Mexico. So for B2, which was the cheapest, is a single story house. We call it case 1. It's only 36 meters square. We also want to analyze the apartment in Mexico because it's less common, but it's common. And it's an apartment unit, which is 4-story. For the traditional case 3, it's a double-story house. We are considering the whole double story as one house. And for the systems of air conditioning, we are using package GX for our cooling set points. We have 25 and heating is 21. Occupancy schedule, because it's a residential house, during the weekdays is 6 p.m. to 9 a.m. Weekend is 24 hours. And also we have a typical summer week from 13 to 19 July, and our hottest day is 27 July. Typical winter is 20 to 26 January, and coldest day is 13 December. So then few things, assumptions before we go into the simulation that we had in this study is that in this study, we only consider one type of climates in the main climates of Mexico, of course, because of the time. And also another one for the apartment building, it's 4-story, but we are only analyzing the top floor, which is the most extreme case, is receiving the most amount of radiation. And for orientation of all the buildings, we are also, because there could be many orientation, but we are considering the most extreme, which is all the main facades and windows are facing east-west. And also the last assumption that we had is that in Mexico, each state has different billing tariff, and we are only considering the tariff for Nuevo Leon. So moving on to the simulation result and analysis, we have our results process. Just to simplify it and tell you how we're gonna talk about it, is that we have 3 cases, case C1, C2, and C3. And we also considering that building envelope is consisted of 3 main envelopes. One is wall, roof, and the openings. So we're gonna simulate, we're gonna optimize each building component, means wall separately, and the rest is basic, roof separately and opening separately. And we choose the most efficient scenario for each component, and then we would make this selection based on total energy and cost saving. So whichever scenario is most efficient in terms of both cost and energy. And then the most optimum of each building envelope is mixed together for each case. And then we have the most optimum combined strategy for case 1, case 2, and case 3. Once we have those optimum scenarios, we analyze the 5 parameters, thermal analysis of the coldest day and hottest day, and also analyzing comfort hours, analyzing energy analysis, and also we are going to look at the annual carbon reduction, and also lastly, the economical analysis, how it benefits the users. So to summary, there are 3 cases, 1 climate, arid climate. We have wall, roof, and window. For a wall, we selected reflective painting, insulation, and PCM. For the roof is the same materials. For opening is double glazing with reflective paint, double glazing with Lowy, and shading. And then we have to make it short form to explain it, because there will be a lot of words. So here is the nomenclature. And also, as you can see, for wall, we use PCM and insulation and reflective paint, but also we can combine the scenarios. So for example, here we have W.I is wall, insulation and reflective paint. Then WPR is wall with PCM and reflective paint. PI is PCM and insulation. So same way for the roof and for the openings. We try to combine the scenarios as well. For the thermal properties of all the materials, for reflective paint, we put the thickness 0.005. Thermal absorptions of most of them are 0.9. And for the PCM only, because we needed to do a sensitivity analysis to understand that, because PCMs are available in different melting point depending on the climate condition, you have to select the best one. So for infinite R that we use in this study and is only available in Mexico, they have melting point at 23, 25, and 29. We tried to simulate all and see how much annually they save energy, and we saw PCM 25 outperform the others. So that's why we use in this study PCM 25 with the thickness of 0.012, which is only 1 centimeter, whereas insulation has a thickness of 0.07, which is 7 centimeters. For the roof was the same material. For window, we have double clear glass, which is a 6 mm glass with 13 mm of air gap. Is the same way for lowy and reflective. It's just that they have the coating on the inside wall. And for the horizontal shading, it's just the external horizontal block of cement. And also to consider that all the cases, this is just case 1 as an example, but all the cases are facing east-west facade, so they are receiving the most amount of radiation. And going to selection of the best scenarios. So to select the best scenarios, first we look at how much is the base case energy consumption and how is the distribution for the energy for cooling, and 9%, almost 60% of energy is for cooling, whereas for case 2 and case 3, cooling energy is more responsible than heating energy. Then we move into selections of most optimum wall for based on annual energy consumption. On the left side, you can see that total cooling energy reduction, and then below is total heating energy reduction per all the scenarios. So we have 6 scenarios for wall. For example, here if we look at only cooling energy reduction, wall with PCM and reflective paint outperformed, and you can see for case 1, case 2, 3, they are following the same pattern, all of them. So and when we look at the heating energy, PCM with insulation outperformed the others, and this is because reflective paint will reflect all the radiation. It won't allow you to for the space to absorb the radiation. So during winter, when you don't absorb the heat, the little heat that sun has, your space becomes cooler, so you don't have much saving in terms of heating. You need more energy to heat down your building. Whereas for the summertime, reflective painting doesn't allow the excess heat to come in, and you are saving more in the cooling side. So what we care here was the total, because sometimes, as we said, if we save on summer but we lose in winter, there is no point. So looking at the total energy saving, we saw that wall with PCM and insulation outperformed other, had the most percentage in all cases, 1, 2, 3, same pattern, and followed by insulation with reflective paint with a little bit of difference. So first is PCM with insulation, then is insulation with reflective paint. Going to improving the roof. So when we applied the same scenarios for the roof only, we saw the same pattern repeating. So for cooling, PCM with reflective paint outperform others, whereas for the heating energy, PCM with insulation, and then again in total, PCM with insulation outperformed others, followed by insulation with reflective paint, which is close, for example, 25% and 23%. And for the openings, we saw that between double clear glazing, lowy glazing, and reflective glazing, lowy glazing outperformed both in terms of cooling and heating, and also total. So we combined it with shading, and we got a saving of 13%, 11%, and 22% for all the cases. Then when we want to select, so now we know how much we saved in terms of energy in all the scenarios for wall, windows, and roof. But then another important thing was the cost factor. So here on top, we can see the cost per square meter for each material, building material. And then we try to look at the cost. For example, if we have the PCM with insulation, the cost for case 1 is 150,000, whereas if we have insulation with reflective paint, the cost is only 50,000. So it's almost 1/3. For all the other cases is more than that. So based on the cost and economical value, we see that insulation with reflective paint is more valuable. But another thing that got us thinking was that the PCM was a good scenario, but due to its cost, we didn't select it. But also the thickness. Insulation has a thickness of 7 centimeters, whereas PCM has only 1 centimeter. So we also did another sensitivity test for the PCM thickness, and we tried to have a similar thickness as insulation. So PCM 25 with 7 centimeters of thickness, and we see that it could save up to 57%, as into insulation is only 42%, and 57% for case 1 as compared to combined strategy of 53. So actually PCM could be much more effective than all the other strategies if it was more economical, and also if it was provided in a thicker in the industry, because now it's only available in 12 cm, and if you want to buy 7 layers, of course it's very expensive. So there's a potential here that we detected. And then so now we selected our optimum wall strategy, roof strategy, and window strategy. Then we want to combine them and also understand the impact of energy efficient configuration cases. The first thing we want to analyze is comfort and thermal analysis. To understand the thermal and comfort analysis, because it's we can't have an average because it's very zone based. We can't have an average of the whole house. We have to analyze per zone, and we try to select one zone and see the most critical zone. How is the impact of this configuration? So for the selection, we look at the solar gain during the summer week and more critical. And we saw that zone 2 in all the cases was most critical. And also looking at the floor plan of, for example, case 1, we can see that zone 2 is coming out, so it's receiving more radiation. For case 2, zone 2 is bigger and it has more openings and windows, so it's also receiving more radiation. There is an explanation why it's more critical, but we selected zone 2. So first thing we analyze is a thermal analysis, just the temperature, and we look at the hottest day and coldest day. So during the hottest day, the blue line shows the outside temperature, the gray line shows the base case, shows the optimum strategy, which is energy efficient case, and the orange line shows the hours of temperature for the base case. And also the green bar you can see is ASHRAE comfort boundary, which is between for summer is 20 to 27. And we can see that for case 1, we see a lot of improvement in terms of thermal. We can see that on maximum, we had an improvement of 8.8 degrees, and average, we improved by 5.9 degrees Celsius, which is a lot. For case 3, we had a bit of a less, but it was we still have an average of 3 degrees Celsius. But in case 2, we don't see any improvement. And we hypothesize that it's because of its altitude, and it's higher from the floor because it's 4 stories, so it's receiving much more radiation than the other cases. So during the hottest day, it didn't have much improvement in terms of thermal. And also looking at the comfort area, none of them drop in the comfort hours, so they are still during the hottest day there is still a need for mechanical system, but with paying attention that this is only the hottest day in the year. And then also we try to analyze the coldest day, and then we saw for case 1, case 2, and case 3, we see a similar improvement, almost 2 degrees Celsius. For case 1 and 3 is 2.5 degrees Celsius of improvement, but still they don't fall into the boundary of comfort, and there is still a need of mechanical system to heat the space. And then we want to look at how much it impacts on the comfort area. For the comfort, we use a PMB method by, it was founded in 1970s by P.O. Fangers. And this PMB method is not just temperature, it's also considering, the formula is considering humidity, airspeed, and radiant temperature, also the human's metabolic rate, the closing insulation. And he tried to have a rating between -3 to +3, whereas 0 is the neutral. From -1 to +1 was the neutral level of comfort. And we tried to simulate our zone 2 spaces to see how much hours of comfort we have in the base case and in the optimum case. So here in the chart, in the figure, you can see the green dots are the numbers, all the hours, the 8,000 hours in a year for base case, and the blue dots are the hours based on PMV for the optimum case or the energy efficient case. And we can see the little bar of the blue bar is the boundary of comfort for based on PMV, which is from -1 to 1. And we can see for case 1, we see that from all the green dots, the blue dots falls a lot in the bars of comfort, whereas case 2 and case 3, they are less within the comfort zone. There are less dots within the comfort zone. Case 2 is less improvement. So looking at the numbers, we see that for zone 2 in case 1, we have 45%, almost half amount of improvement in comfort. For case 2 and 3, we have 32% and 38% improvement in terms of hours. And then we move into seeing the impact of our optimum case in terms of energy, how much energy we are saving. So on the top here, we can see that for wall and roof, we have reflective pane insulation. For openings, we have low E glazing and shading. Down below, we see the construction detail of how is it built for the roof, the wall, and the windows. And looking at the figure, we can see the annual energy consumption of a base case and the optimum case. As you can see here, the blue color shows the base case cooling energy consumption, and the orange shows the optimum case cooling energy consumption. So we can see that it almost reduced by 1/3 for cooling energy consumption, and the heating reduced by 1/4. So cooling reduction was 76% in total and heating 21%. However, for the total, we have almost half, 53% of energy saving. So here, cooling energy reduction was more, but for case 2, we see that the cooling reduction was 50% and heating was 66%. But on total annual energy saving, all had a similar saving of 55%, very close. And for case 3, we see 60% saving in cooling, 48% saving in heating, and in total, in a year, we have saving of 58% in the building. So they all have almost 53, 55, and 58%. So we want to translate that into how much emissions are we saving by reducing this much energy. So based on Commission of Energy in Mexico during 2019, for every megawatt hours of electricity, there is 0.505 tons of carbon is emitted, which we want to calculate based on kilowatt hour. We have 0.505 kilogram of carbon per kilowatt hour. So based on how much energy we save, we can see here for case 1, we save 1,580, almost 80 kilogram of carbon saved. For case 2, we see 2,800 kilogram of carbon and almost 3,000 kilogram of carbon for one house. If we apply this scenario, if we want to translate it into how many trees are we planting if we save this much carbon, 75 trees works as 1,580 kilogram of carbon. So for just one house, we are planting this much tree. And imagine if we are extrapolating it for the whole city, how much trees are we planting? Or for the case 2 is 133, and for case 3 is 143 of trees. Also, with regards to Mexican total energy supply, one of the main contributors is oil, which is non-Mexico. So we want to translate that into how much barrels of oil are we saving every year for one house. And we can see that for every barrel of oil, which is 42 gallons, for case 1, we are saving 2 barrels less. For case 2, 3.2 barrel, and for case 3, 3.5 barrels of oil less we are using for one house. And at the end, we also analyze the cost for the users and the investors to understand, okay, how much cost they have and how much, when are they getting back their investment and how much they are earning back. So for case 1, we see that annual energy cost reduction is 8,500. For case 2 and 3 is more because it's an apartment and that one is a double story, is a bigger house. So it's 15,800, 16,900. And the material cost almost for all of them is around 50,000 Mexican pesos. So the period of return for case one, because it has a lower level of cost, so in terms of energy cost, so it will return in 6 years, almost 6 years. For case 1, 2, and 3, almost in 3.5 years, they will see a return of their investment. So after that 3.5 years, they have a profit of almost 15,000, 16,000 every year. So they are profiting after that. So I think they have a motivation to apply such scenarios. And in conclusion, we want to conclude that, so for the wall scenarios for us to select, we saw that PCM with insulation outperformed others with 900 kilowatt hours, 1,700 and 1,400 for case 1, 2, and 3. But with regards to our cost analysis, we saw that wall with insulation reflective paint was more optimum. It save energy a little bit less, for example, from 900 to 810 kilowatt hour, but in terms of cost, is much more effective. And for the PCM, we found that that because of its thickness, low thickness, we saw a lower impact. But if we increase its thickness, we will have, for example, for case 1, we can have the energy improvement of 57%, which is a lot. And also, if we could have a better cost for PCM. And for glazing, we saw that actually glazing is responsible for a higher amount of cost in the building envelope. And also, we saw that low E glazing outperformed others. And we can save up to 22% for case 1, 18 and 13% for case 2 and case 3. And then overall, we saw that it's desirable for all the cases, case 1, 2, and 3, to have the same scenario for wall and roof reflective paint with insulation, and for the openings, low E glazing with shading, horizontal shading. And we can save up to 53, 55, 58% for case 1 to case 3, which is almost half for all cases. And then we want to translate these parameters into a ratio of 1 to 10 instead of all the. So that case 1 had the most amount of saving in terms of cooling energy. As you can see here, compared to heating, we saw that case 2 has the highest amount of saving. And in terms of carbon emission, almost since all of them were reduced to half of their consumption, so they saw a similar amount of carbon reduction from 1,500 kilogram for case 1 and 2,800, almost 800 for case 2, and 3,000 kilogram for case 3. With regards to thermal performance, we saw that for case 1 and case 2, case 1 and case 3, we saw a better improvement in terms of the hottest day, whereas case 2, we didn't see any improvement in the hottest day, also maybe due to its altitude. However, for the cooling, the coldest day, we saw that all the cases had a similar improvement of 2.4 or 2 degrees Celsius. And with regards to comfort, we saw that also case 1 had the most amount of improvement by 45%, and the others were only 33 and 38%. For the payback period of years, we saw that also case 1 had the highest amount of longest amount of payback, which is almost 6 years. It's also because it has a lower demand for energy consumption. And for case 2 and 3, we saw 3 and 6 and 3.5, almost 3.5 years of period of return, respectively. Finally, what we recommend for the future researchers and the future work is that one of the things is that PCM has a lot of potential, but especially in semi-arid climate, and we saw that if we could increase its thickness, we could save up to 57% instead of 53%, and we are using less material because it's not combined with any other scenarios. But because of its high price, it's less applicable right now, but it has a high potential for the future if they invest more in it for energy efficient. And also, secondly, we think that to extrapolate the result and understand how much the government could save in the whole Mexico, they could do other climates of Mexico, they could study and understand what is the cost and emission reduction in the whole country. And then finally, We took a numerical approach and we simulated, so we think that there could be an experimental approach of all the scenarios application, which they could investigate all kind of the parameters that we analyze, but in terms of experimental approach. So thank you so much for listening, and I'm here to answer your questions.